Hello everyone, my name is Professor Anil Fernando from the Department of Computer and Information Sciences in Strathclyde University in Glasgow, UK. So today I'm going to talk about semantic communication for secure image transmission. Before we start the presentation, I would like to give a short introduction to my research work and research team. And at Strathclyde, I'm leading the multimedia research group with 20 plus researchers working on different aspects of communication, semantic communication, image and video compression for transmission, noise modeling in semantic communication applications, multimetrics for media applications, machine-to-machine and 6G media applications for task-oriented semantic-based communications. And in the other group, people are working on video coding and communications and machine learning for different applications. And finally, how machine learning and image and video processing techniques can be used for future digital advertising applications. And this is a snapshot of how people are working on different domains. A lot of people are working on media communications, which involves semantic communications, video communication, image communication, and so on. And some people are working on energy management, how energy can be used, utilized in a more efficient way using some machine learning techniques. And next generation networks is another area of my research. And finally, insurance and finances, how machine learning can be used in these domains to optimize their uh, uh, systems. And finally, some people are also working on digital health, mainly vision and processing and image processing techniques can be used with AI for better info, how to get the better informed decisions in digital health applications. And since this presentation is all about semantic communication, so there are a lot of people working on semantic communication and related applications, and 6, 7 people are working in these domains. And for those who don't know anything about semantic communication, so I'll just start with the basic introduction to the communication system. In any communication system, we have a source, which is like video or audio or image, and then we use some kind of source encoding techniques to remove the correlations between the information bits or pixels, and then we use the channel encoding. We deliberately put some information to protect the data uh, when the information is transmitted through the channel. So the channel will introduce noise to combat that. So people have been using channel encoding is a way to protect the information during the transmission. And between the channel encoder and the channel, we have a modulator, a digital modulator, and then digital demodulator, and then channel decoder, source decoder, and the destination. So Shannon and Bevier in 1949 and 1952, and they have defined 3 problems in communication. The first layer is defined as the level A, technical problem. So in the technical problem, people have been looking at accuracy of transference of information from sender to the receiver is guaranteed in the bit level. So this is the foundation that we have been experiencing today for the last 75 years, how the communication is happened based on the Shannon's definitions of technical problem formulation. So they also define 2 other layers, semantic problem and the effectiveness problem. The semantic problem by definition is the interpretation of meaning of the information and how meaningfully that information can be transmitted and received as a receiver as compared with the intended meaning of the sender. So that was defined as the semantic problem. And finally, the level C is defined as the effectiveness problem and how success with which the meaning conveyed to the receiver leads to the desired content. So basically, what the information we transmit from A to B may contain some kind of information which leads to an action. For example, if somebody is coming behind to shoot you, so the message is like you have to look for a place to hide uh, from the protection. So this kind of information is defined as the information critical for the action. So that is defined as the effectiveness problem. So based on this foundation and the future of communication will be different, because now previously people have not been looking at this level 2, level B and level C, mainly because of we didn't have any computational power to understand the meaning of the information. Now AI has gained quite a lot of advance compared to what we had before, and therefore we should be able to understand the meaning of the information, and then we can go to the semantic problem, and effectively we can go to the effectiveness problem, which will guarantee how to utilize the communication resources more effectively to transmit the information from place 1 to place 2. So based on the channel, so he defines the channel capacity theorem, which is the channel capacity is equal B log 2 of 1 plus S. So N is the 1 is the signal noise ratio. Therefore, depending on signal noise ratio and the channel bandwidth, channel capacity is fixed. So therefore, we can't go beyond that. So this is the problem that we have been saturating at the moment. So channel capacity can be increased. So there should be a new way of sending the information within the level B and level C, mainly for like machine to machine communication. So this is how the semantic communication system is being proposed. So we have a source. Basically, we have an additional layer of information compared to the classical system that we had presented before. Between the source and child encoder, there's a source semantic encoder, and then between the destination and channel decoder, there's a semantic decoder, which is combined with another contextual information. That contextual information is defined either semantic noise free or with some semantic noise. So sometimes, if you try to improve the semantic noise, reduce the effect of semantic noise, we have to sacrifice a lot of channel bandwidth again. When the semantic noise is zero, so that means virtually we are coming back to the technical problem. So this is the focus of the discussion today. So we have the source, semantic encoder, context information, semantic noise, destination, and semantic decoder. So the objective of this presentation is how secure communication is linked with the semantic communication. So to start with the introduction, we have the input data, source encoder, channel encoder, wireless channel, channel decoder, and the source decoder. So that's how the semantic system works. And then, so we will, during this presentation or during this work, what we will be looking at is like how the semantic encoder and decoder, is there any inherent security features embedded with semantic encoder and decoder compared to the technical level encoding and decoding? So the aim is to investigate whether the semantic communication has inherent security features and to understand how the architecture of these systems contribute to the protection of transmitted data from unauthorized reconstruction. And also, additionally, to explore and propose strategies that users can adopt to enhance the security of semantic communication systems, ensuring greater resilience against potential attacks. So, if you go and search about the literature on these domains, there's not much work has been done on semantic communication until recently. So, in the last 2 years or 3 years rather, people have started looking at the semantic communication problem. Uh, there are some research is being carried out now how semantic communication can be better implemented compared to conventional communication, and people have proposed some of the ideas as well for image communication and data, sorry, text and speech transmission. So motivation of this study is to is the lack of synthetic systematic investigation into the inherent security of semantic communications. And then the research question is, can semantic communication systems secure data without any cryptography methods? So if you go into the problem statement, traditional communication is heavily depend on cryptographic layers for ensuring data security. And in semantic communication, we try to understand whether is there any protection, natural protection from semantic encoder and decoder architecture to protect the data so that we can minimize the use of cryptographic layers for end-to-end communication. So therefore, the research objective is can semantic communication systems inherently secure data transmission to design an architecture alone, or we need to provide some kind of security like in the conventional communications. So the key aspects of this study is to find out the impact of encoder architecture differences, role of identical initialization of states in the architectural versions of the encoder and decoder, effects of controlled environments with identical architecture, training data, and initialization. So in this proposal, what we have done is we have tried to use an autoencoder based system of one of our previous work on semantic communication. So therefore, we use autoencoder as a semantic encoder, and autodecoder is used as a equivalent semantic decoder. So back-to-back connection of autoencoder and decoder through the communication channel is used for this experimentation. And we assume that channel will be ideal and therefore no errors will be identified by the technical layers. So if you go into the related work, semantic communication, like I told you, that nothing much has been done for until recent past. So during the last 2-3 years, people have started looking into this problem and then limited investigation into inherent security beyond this encryption and traditional cryptographic methods have been explored. And encrypted semantic communication systems combine cryptography with semantic communication, but often assumes adversaries have similar decoder architectures. And the research gap, therefore, we have identified is a lack of studies examining security from system architecture, training conditions, and autoencode based semantic communications and mismatches. So during this study, what we have done is, so we have tried to understand the current framework and security gap. So we have conducted a thorough literature review on this domain. Nothing much has been proposed other than one work which has assumed some unrealistic scenarios. In this study, what we have done is we have assumed the realistic scenarios of encoder, uh, and decoder and the training process, training data. So there are four different things that we have to consider. All these four different things can be hacked by an intruder, and then we can investigate how difficult is for the intruder to hack the communication system using different scenarios. So what we have done is, so this graph, this figure shows how we implemented the system. We have the input image, then we have the autoencoder, which is used as semantic encoder, then the channel, then semantic decoder, and output image. And then Alice is the transmitter in this case, and Bob is the receiver. And then Merlin Milroy is the intruder, and he tried to mimic the encoder and decoder architecture and then try to steal the information to generate this output image. So we have assumed that the encoder, decoder, and the dataset and the initialization process. So all these four different things, we assume that availability of 1, 2, 3, and 4, and then see how the the results will behave. So to mimic the machine person, this is like a task-oriented application, as you can see. Like since the machine is taking decision, we have used a CNN classifier to understand the output images. In this case, we have used two different data sets, but in this presentation, I'm using a very simple data set, means data set number classification. So we are transmitting 0 to 9 numbers many times, like thousand, more than thousand times we transmit, and then we have reference scenarios, reference autoencoder, which doesn't have any kind of artifacts, like we train the autoencoder and then transmit the information, and then we try to test the accuracy, which is like 98.6% accuracy. And then in the same scenario one, we have assumed that encoder is not known, but the decoder is known. And in the second scenario, we assume the decoder is known and also the initialization is known. And then in the final scenario number three, we assume encoder, decoder, and the initialization process is also known. So you can see that from the first two scenarios, when the decoder is known and the and encoder and the initialization decoder and the initialization process is known, so the test accuracy is very low, below 10%. But as soon as the encoder is also available, you can see this jumps to 80% accuracy, which indicates that encoder is more powerful. Knowing the encoder is more powerful than anything else. But even with everything is known to the receiver, in this Android, the intruder, so still there is about 20% chance that information cannot be retrieved correctly. So these are some of the outputs of Alice uh, in each scenario, and then output of the Melroy, which is the intruder on the right hand side. You can see that in scenario one, nothing can be decoded perfectly. A lot of some kind of garbage images, numbers cannot be detected. In scenario two also, nothing much can be decoded, but in scenario three, some of the information can be decoded, which leads to a better accuracy. But this indicates that there is still, when everything is known to the include the architecture, encode architecture, decode architecture, and the initialization process, the data set which is for training. If everything is known to the intruder, so there is about 80% chance that the intruder can detect these numbers. But when it comes to a general image like uh, if human face or any other images, the intruder will be having a lot of difficulties. In the second phase of our work, we have used different images, but still the intruder has some kind of ability to understand these images, uh, but not like in number systems. Number systems are easy to detect, so that leads to a higher prediction when everything is known to the intruder. But the basic information is semantic encoder and decoder architecture has some kind of inherent security embedded with the systems. So which leads to our research, like we only need little security to be provided compared to the classical systems. So exploring more data types, architectural optimization, and adversarial threat models are our future work. So we'll be focusing on these domains in the next phase of our work, together with further generalizing the semantic encode decode architecture to other different domains as well. So that leads to the end of this presentation. Thank you very much for listening to this presentation. If you have any questions, please feel email to me. My email address is given in the slide, and hopefully we can start some kind of collaborative discussion and collaborative research in the future on this interesting topic. Thank you very much again, and have a nice day.